In this video, we will look at the position vector, the velocity vector, and how the velocity vector can change. The position vector is simply the vector that takes you from the origin to a particular position with coordinates x, y, and z. And thus, the position vector is given by xi hat plus yj hat plus zk hat. Let us look at an illustration of this. If we have a point particle moving, we can describe its position by the position vector. Here's an example in 2D. This shows you the path of a particle in the xy plane. Notice there is no time axis here. This is the full trail of the particle in the xy plane. At time t1, let's say it's over here. Then this is the position vector from the origin to the point where the particle is. Perhaps at some later time, t2, it's over here. Then this is the position vector at time t2, which we can write as the position vector at time t2. So we can express the 3D position vector, which is possibly a function of time, as the sum of these three 1D position vectors, each of which is a function of time. So x is a function of time, y is a function of time, and z is a function of time. We can refer to x of t as the x component of the position vector, y of t as the y component of the position vector, and so on. The displacement is the change in position, that is, r final minus r initial. And it points from the initial position to the final position. Displacement, remember, is a vector. In this case, if this is the initial position and this is the final position, then the displacement points like this, from the initial to the final. We can express that in terms of r1 and r2 as minus r1 plus r2, because that has the same effect of going from here to here. The velocity vector is easiest to understand when we first look at the average velocity, which is the change in position over the change in time. Just remember, though, that now the position is given by the position vector, so we are talking about the change in the position vector over the change in time. But 1 over delta t is a scalar, and so all it can do is scale the vector delta r. It cannot change its direction. So v average and delta r will have the same direction, but they'll have different magnitudes and different units. Delta r is in meters, but v average, which is delta r over delta t, is in meters per second. Let's get an idea of what that looks like. Say that this blue line is the path followed by a particle. We consider 2 points, here and here, and we look at the displacement and the velocity, the average velocity, between those 2 points. That is the displacement. What happens as we shrink the time interval between the 2 points? So now the 2 points, you might see the little red dots, the 2 points are closer, and thus the displacement is smaller. But the velocity, remember, is delta r over delta t. So even though delta r has a smaller magnitude, delta t is also smaller. And so the ratio, delta r over delta t, which gives you the velocity, can still be large. Here, this red arrow is the displacement, and this green arrow, which goes from here to here, is the velocity. You can see that they have the same direction, but they are scaled differently. As we continue shrinking the interval, we find that the direction of the velocity vector, the instantaneous velocity, is achieved in the limit as delta t goes to 0, and the direction of that velocity vector is tangent to the curve. So at this point in the curve it points like this, at this point it points like this, and so on. This is always true no matter what the shape of the curve. The velocity vector will be tangent to the curve. So, as delta t goes to 0, our ratio of delta r over delta t becomes a derivative, dr over dt, and our average velocity goes instead to the instantaneous velocity. And as we have mentioned, the direction of this instantaneous velocity is tangent to the trajectory or path of the particle. This is tangent, this is tangent, this is tangent. These are the velocity vectors at these three different points along the trajectory or the path of the particle. And so, since the instantaneous velocity is given by the derivative of the position vector, we can write it as dx over dt I hat plus dy over dt j hat plus dz over dt k hat. In other words, it is simply the x component of the velocity times I hat plus the y component of the velocity times j hat plus the z component of the velocity times k hat. By taking these three components and using the unit vectors, we can put them together into a single velocity vector. We know that acceleration is the rate of change of velocity. Now that we are working in 2D and 3D, and velocity is treated as a full vector, there are two ways to change the velocity. Since velocity is a vector, like any vector, it has both magnitude and direction. And so, you can change the velocity vector by changing its magnitude, or you can change the velocity vector by changing its direction. And there are two corresponding types of acceleration. There's an acceleration that changes the speed, that is the magnitude of the velocity, and there is an acceleration that changes only the direction of the velocity, but leaves the magnitude alone. Here's an example. Try and answer this question. A point particle, shown here by a black dot, is moving. Its velocity vector is shown by this blue arrow, and the acceleration by this green arrow. What is the particle doing at this time? Is it speeding up and turning to its left, speeding up and turning to its right, slowing down and turning to its left, slowing and turning to its right, or only turning and not speeding up or slowing down? Pause the video and try and answer the question by yourself. We will now discuss the answer. The simplest way to answer this question is to break up the acceleration into two components. One component lies along the line of the velocity, and the other component lies perpendicular to the velocity. We can see that these two accelerations added together give us the original acceleration. So, what are the effects of these two components? This component lies along the line of the velocity and points in the same direction as the velocity. So, it will help speed up the particle. This component is perpendicular to the velocity. It can't speed it up or slow it down, but it can change the direction. And we can see, since the particle is heading this way and the acceleration points this way, the particle's path will change from this to this. And so the particle is turning to its left. And so we say that the particle is speeding up and turning to its left. So, we have learned that there are two types of acceleration, and the velocity is always tangent to the curve, but the acceleration can have a component which is tangent to the curve and thus lies along the line of v, and a component which is perpendicular to the curve and thus perpendicular to the velocity. So, even though v is always tangent to the curve, a does not have to be tangent to the curve. The component of a which is tangent to the curve is called the tangential acceleration, and the component which is perpendicular to the tangent is called the centripetal or radial acceleration. Remember, the tangential acceleration lies along the same line as v, and so it will either speed up or slow down the particle. That is, it changes only the magnitude of v, the speed. It cannot change the direction. The centripetal acceleration, denoted by AC, is also called the radial acceleration, AR, and this can only change the direction of v. It cannot speed it up or slow it down. It can only change the direction, and so it lies perpendicular to the velocity. Here's an example we have seen before. This is a motion diagram showing the motion of a pendulum. It swings from one end to the other. The blue arrows show the displacements and are thus also proportional to the velocities. We know that the acceleration is related to the change in velocity, that is, velocity after minus velocity before. If we look at point 0, when the pendulum starts its swing, its initial velocity is just 0. And just after that, its velocity is tangent to the curve. The difference in velocity, that is v after minus v initial, is in the same direction as the velocity. And so we can say the acceleration is only tangential at point 0. Similarly, at point 8, the particle comes in with some velocity and then comes to a stop. So, velocity after is 0, and this is the velocity before. If we look at the change in velocity, that is velocity after minus velocity before, we see that this acceleration points exactly opposite to the velocity. So here, the velocity and the acceleration lie along the same direction. Their acceleration is tangential and helps speed up the particle. Here, the velocity and the acceleration lie along the same line, but point in opposite directions, and so the acceleration helps slow down the particle to a stop. What about here? Just before reaching this point, the velocity is like that, and just after, the velocity is like that. If we look at the change in velocity, that is velocity after minus velocity before, what do we get? Let's make this a bit clearer by labeling them. This is velocity v45, and this is velocity v34. But what we want is v45 minus v34. v45 And this now is minus v34. If we add these two vectors now, we have v45 minus v34. And that result points straight up. And so the change in velocity points straight up, which makes sense because the velocity has gone from pointing to the right and down to pointing to the right and up. And so the change is pointing up. And so the acceleration at this point points up. Since it is perpendicular to the tangent, we can see that the acceleration at this point is purely radial or centripetal. There is no tangential acceleration at this point. The speed is not changing at this point. It is only changing direction, and so the acceleration is purely radial. At the other points in between, there is a combination of both radial and tangential accelerations. Here's a question in 2D kinematics. A dog running in an open field has components of velocity vx equals 3 meters per second, vy equals minus 2 meters per second, where east is the positive x direction and north is the positive y direction. The dog spots a squirrel and accelerates for 5 seconds at 0.6 meters per second squared at 30 degrees north of east. We are asked to answer the following questions. What is the final velocity vector of the dog? What is the final speed of the dog? And what is the final direction in which the dog is running? Pause the video and try and answer these questions by yourself. In the next slide, we will discuss some of the answers. Once again, pause the video and try and answer the question by yourself. We will now start discussing how to solve this problem. Whenever dealing with any kinematics problem, whether 1D, 2D, or 3D, first start by listing your knowns and unknowns. Here we can put x initial is equal to 0, y initial is equal to 0, vx initial is equal to 3 meters per second, vy initial is equal to negative 2 meters per second. What we need now are the x and y accelerations. Since the acceleration makes an angle of 30 degrees with the x-axis, remember it is listed as 30 degrees north of east, so that is 30 degrees above the east line, that is 30 degrees above the x-axis, we can find the x component by doing 0.6 meters per second squared times cosine of 30, which gives us ax is equal to 0.52 meters per second squared. And similarly, ay will be given by 0.6 meters per second squared times sine of 30, which gives us 0.3 meters per second squared. And the last thing that we note is that the time is equal to 5 seconds. Now, we want the final velocity vector of the dog. To do that, we need to find the final x velocity and the final y velocity, that is the x component and the y component. We use the constant acceleration equations because the dog's acceleration is constant. To find the x component, we use the equation v final equals v initial plus at, but specialize it to the x direction. And so we have vx final is equal to vx initial plus axt. Notice how we do not use the full acceleration, but only the x component. Since we have our list of values, we can plug them in. So for the Vx initial, we plug in 3 meters per second. For Ax, we plug in 0.52 meters per second squared. For t, we plug in 5 seconds, and so the units of Ax times t will be meters per second. We calculate, and we get Vx final is 5.6 meters per second. Similarly, in the y direction, we use Vy final is equal to Vy initial plus Ay times t. Again, we do not use the full acceleration, we use simply the y component. Once again, plugging in values, we have minus 2 meters per second as Vy initial. Ay is 0.3 meters per second squared, and time t is 5 seconds. We calculate and find Vy final is negative 0.5 meters per second. So, what is the final velocity vector? Since we asked for the vector, we should give it with the components and the unit vectors, I hat, j hat, k hat, so on. And so, we see that the v final vector, that is the final velocity vector, is 5.6 meters per second I hat minus 0.5 meters per second j hat. Notice a few things. One, this is a vector. We have combined the components with the unit vectors to give an overall object that has both direction and magnitude. All right, it tells us how fast it's moving in the x direction and how fast it's moving in the y direction. Notice that we do not use any commas. If we are using I hat and j hat, we don't need any commas. We just add the various components as long as we keep the I hats and j hats there to keep them distinct. This is the velocity vector. In general, when you are asked for a vector quantity, present your answer in vector format, that is I hat, j hat, k hat, with appropriate components. From this, if we now want to find the magnitude of the velocity, that is the speed, we can simply square the x component, square the y component, add those, and then square root them. And that will give us the magnitude of the velocity, that is, it will give us the speed. If we want to find the direction, well, since this is motion in the xy plane, we can use inverse tan of the y component, Vy, which is negative 0.5, over the x component, Vx, which is 5.6. The inverse tan of that ratio, negative 0.5 over 5.6, will give us the angle that this velocity vector makes with the x-axis. However, let me remind you, inverse tan only works if you are working with a two-dimensional vector. It will not work in 3D in general. That's the end of this video. I'll see you in the next.